So we will delve further on convexity and quickly run through conditions of convexity through first order relationships as well. Um, yeah, so this is the outline. We'll kind of reflect why we talked about convexity, or even if the function is non-convex, we showed that the domain often has to be convex. That means a notion of convex sets becomes important. Convex sets are important also from the point of view of how they relate directly to convexity of functions. Um, we started with the separating hyperplane theorem, kind of give a hint for it, but I'll delve on it further today, and then take up convex functions a little bit more carefully, their properties, and how do you understand basically the convexity of machine learning loss functions. Then we delve into basic subgradient calculus, the calculus of gradients, and for non-differentiable functions, the notion of subgradients which exist if the function is convex. And that itself is broken down into the direction vector and directional derivative and so on. Finally, look at convex functions and their epigraphs. There's a notion of quasi-convexity, which is kind of inspired by the notion of subgradient. And then we look at convex optimization problems. So this is like the trajectory. For convex optimization problems, again, we revisit the calculus of subgradients. Okay. Um, so we recap that we left off at this. We talked about convex combinations of a bunch of points x1, x2, xn for all possible thetas, all possible convex combinations is basically the convex hull. And we have enough motivation to see that it is a convex set. Convex hull is always a convex set. Right? So should S be always convex? Looks like it's always convex. But then we are trying to um, also delve into what does this lead to? What is the implication? Okay. So is there a notion of supporting hyperplanes that are characteristic to convex sets and not found in non-convex sets? Right. So supporting hyperplane to basically would mean that at a point, every point in the set there's a tangent, and every right, and it should happen that all the points in the set lie on one side of that tangent. But as is possibly visible in this example, it's if my set is like this, and if I pick a point here, I can't come up with a supporting hyperplane, right? But if moment I create a convex hull, this is my new set. This also belongs to the set, and I can talk about supporting hyperplanes, right? So it's easy to visualize the close correspondence of supporting hyperplanes with convexity of sets when we discuss convex hulls. Right? So what is your hypothesis? What do you think will happen? What could I state as a potential theorem? Anyone? I kind of hinted there, right? Supporting hyperplanes are characteristic to convex sets and not found in non-convex sets. Yes. It's okay, speak up. I mean, not far from what we are already written on the board. So let me start and you can complete. So theorem. If C is a convex set, then for and then at any point x in the this is the boundary. Okay, it's called the boundary of C. This partial sign later on will also denote something called subdifferential. but for now, it's just a boundary. To the boundary of C. And what should happen at any point X in the boundary of C? There should exist a supporting hyperplane must exist. And what is supporting hyperplane? Inter that is C is going to be a subset. Actually, C or the closure of C. Closure of C means C including its boundary. C will be a subset of one half space defined by the hyperplane. One of the half spaces defined by the hyperplane. So if it's here, this is half space, right? This half space defined by this hyperplane. Right? This, let's give it a name, supposing hyperplane. H. So H at the point X. So the set C should lie in one of the half spaces. Simple. Very intuitive. So obviously, if you want proof, I have in my Moodle, I would like to remind that, in Moodle, I keep so I put the recording and then I also put a whole bunch of links. So you can, for some of them are, many of them are optional reading. Some of them are like homeworks, like what I'm discussing right now. So, okay, anyways, coming back. You understand the notion of supporting. So please do try and attempt homework, simple problems like this. Okay. So what about the convexity of S? Yes, it is convex, and I hope you did this homework. It is, you can show by first principles that if any bunch of points or even pair of points x1, x2 exist um, in the convex hull of S, then all their convex combinations must also lie within the convex hull. So all you need to do is take this theta y1 plus 1 minus theta, say theta 1 y1 plus 1 minus theta 1 y2, which is x1 times lambda 1, and then basically show that plus 1 minus lambda 2 theta 2 z1 plus 1 minus theta 2 z2 will yield you a convex combination of 2 points, which are already in the convex hull. Okay, so I've written that in text. Verify that we're substituting for x1, x2 terms of y1, y2, z1, z2. The new combination still convex in y1, y2, z1, and z2. So we may have four thetas, right? Theta nu 1, theta nu 2, theta nu 3, and theta nu 4. And you have to show that they sum up to 1. Not difficult at all. Okay. Okay, so and so you'll have to basically show, I don't think you're right. Basically, you'll have to show that there'll be these 4 components which sum up to 1. It's very simple. Okay. Okay. The convexity of convex is guaranteed. S need not be convex, even for its convex hull to be defined. Okay. Now, based on this so-called supporting hyperplane theorem, one could come up with a separating hyperplane theorem, which is if C and D are disjoint convex sets, then you can actually come up with a hyperplane which separates the two. Okay. So if this is C, this is B, you're guaranteed a separating hyperplane. Need not be unique, right? So while I've shown one separating hyperplane, not difficult to come up with a bunch of others. This is also separating hyperplane. This is also separating hyperplane, right? Now, if the sets are not convex, what happens? The set is like this, right? And you have D. Now you see that C and D, C prime, D prime, they are disjoint, but there's no separating hyperplane, right? So what does support vector classification do? It says that, well, if you project these points C prime and D prime in some higher dimensional space, then there is a supporting hyperplane in that space, right? Yes, so this is this can be a separating hyperplane. There's a separating hyperplane in some higher dimensional space into which points in C and D are mapped. I mean, life also we have this experience, right? You may be in some frame of mind and you don't feel hungry, but you just feel elevated when you go into another frame of mind. So, when dimension of your thought process changes, what appeared to be very intangible becomes tangible. So this holds, here very interesting analogy, I thought. However, strict separation requires additional assumptions. Strict separation would mean that the hyperplane does not touch any either of C or D. Okay, so C, if a C is closed and D is a singleton, then you can assume, I can assure that there is a strict separation. Okay, so this is just illustration of what I was trying to say. This is an example of strict separation, right? And what does open? Open close means? Open means that the boundary is not a subset of C. For example, if I just remove the boundary here, just the interior of C is basically open set. Interior of C is an open set, right? So if C is closed, right, then and a certain, you basically can show that there is strict separation is possible. Okay. Anyways, this is not the main topic of discussion, just a side point, strict separation. But let's understand how the separating hyperplane, supporting hyperplane theorem is basically a consequence of separating hyperplane theorem. A supporting hyperplane to set C at boundary point x naught, right? Basically, is separating the set C from what? What is the separating? So how do you view a supporting hyperplane as a separating hyperplane? So could you think of the interior of the set C as being separated from X naught by the supporting hyperplane? On the left hand side, I showed a supporting hyperplane, right? Here is a separating hyperplane. My question is, can you show that supporting hyperplane is a special case of separating hyperplane? So if you have X naught on the boundary and you're trying to separate X naught, so let me show it here. C, and this is X naught. Now I take the interior of C. All I'm saying is the interior of C is separated. Can we view interior of C as being separated from X naught by the supporting hyperplane? Not strict separation, just separation. Okay. Hmm. So your point is, can we not say, well, any connected subset of the boundary? Why only the point X naught in the boundary? Any connected subset? Yeah, as long as you ensure that the connected subset on the boundary is also convex. Right. Yes, but it must be in the boundary. A straight line, if it's not in the boundary, then again, well, I mean, it doesn't have to be. You're right. It basically should. It should subsume the boundary, some subset of the boundary. Okay, so this is exactly what I was trying to say. At least let's take the simple example. If I have X naught here, then I know that if I have separating hyperplane, then that separating hyperplane ensures that A transpose X naught is greater than or equal to A transpose X for all points in the interior of X. Right? So all points in X, but all points also in the interior of X. Right. Okay, so yeah, unlike last year's class, we are moving a little fast with intuitions here. Now, let's take some more examples of convex sets. Euclidean balls and ellipsoids, they're convex sets. So, a Euclidean ball with center XC, this is XC, and radius R. Now, in the case of Euclidean ball, right, R is going to be the same uniform. So XT plus RU such that norm of U is less than or equal to 1 is one way of writing it, or X minus XC norm, 2 norm is less than or equal to R. But what happens if instead of the 2 norm, we use a slightly different norm? What we'll see later as matrix induced norm, or differently put, right? This is what I mean by matrix induced norm. So X minus XC, P inverse X minus XC. I've just put a P inverse in the middle. Right? So a ball, a Euclidean ball, can be written differently as X minus XC transpose X minus XC is less than R, well, square root if you want, or less than equal to R square. But an ellipsoid is x such that x minus xc transpose, but I'm putting a p inverse x minus xc is less than or equal to 1. This 1 is basically a rescaled version of R, where I've absorbed the scale components into P. We don't want unnecessary degrees of freedom. Right? So you see what's happening here. You're just taking this, a ball, and rescale, rotation, all of that is happening through P inverse. P inverse is rotating and also rescaling. Okay. So yeah, you could also, if you, this is also an ellipsoid. How would P inverse look like for this ellipsoid? Axis aligned. Yeah. Right. So this, there's no rotation. Okay, so there's this diagonal. Whereas in this example shown on the board, it'll have off diagonal non-zero entries. Okay. Now there are other representations also. XC plus AU is another representation, such that 2 norm of U is less than or equal to 1. Okay, so this is not very different. In fact, you can show a relation between A and P. So what you're saying is I'll start with my XC. I'll add this unit vector or less than unit vector. I mean, unit vector. Let's take the case of norm U is 1. But that vector I'm going to rotate and rescale. So it's equivalent, right? So yeah, I'm just saying I'll take this XC and my U, which ordinarily was here, let's say. Now I have AU, which goes all the way. Rescaled in different directions. What is the relation you think between A and P? Guess.
P eigen decompose P and then multiply value for the.
So your hunch is it will have something to do with the eigen decomposition. You're right. So that's one reason P is a symmetric positive definite matrix. Okay, so P cannot be an arbitrary matrix. His point is P should have some eigen decomposition which will give you A, right? So A need not have any such property, but P needs to have this property. P must be symmetric positive definite. That's how that's what SN plus plus mean. Positive definite basically is strictly positive definite. What does it mean? All the eigenvalues of P are strictly greater than 0. So I'll just try and show this depiction here. Okay, so right, so symmetric positive definite would mean eigenvalues greater than 0. X transpose, which means X transpose Px would be greater than 0. So that will ensure that your translations are meaningful. The scaling and translations are meaningful. Okay. So now, what is the connection between yeah A and P? It turns out that A is like P square, a P square root. Okay. So you can actually verify that by substituting. A is like the square root of P. But to get the square root of P, you can use the eigenvalue decomposition and you exploit the positiveness, strict positivity rather, of the eigenvalues. Because if P didn't had a negative eigenvalues, you couldn't take the square root. Square root basically means that A into A should give you, sorry, yeah, A into A should give you P. Okay. Yeah, but otherwise, this is the interpretation we have. Basically, P is bringing about non-uniform scaling and rotation. So A must also, one more point is A must be non-singular. What does non-singular mean? Sorry? Determinant should not be 0, which means full rank. That comes by virtue of the fact that basically A into A should give you P, which requires to be a symmetric positive definite matrix. Because what will happen if A did not have full rank? If A did not have a full rank, if you take A into A, it's possible that some of the eigenvalues corresponding to the P matrix could be 0. Okay. Then now we can try and generalize this notion. See, here I've just defined something called P induced or P inverse induced rotation and scaling. So this is basically a new norm, a different kind of norm, right? I could even say that my ellipsoid is a P inverse induced norm ball. Or matrix P inverse induced norm ball. So we can have a more generic notion of a norm. What is a norm? A norm is a function that satisfies that positivity or rather non-negativity, and it should vanish only if the point is 0. Second is that if you have any scalar alpha, you multiply it, take the norm is basically amounting to multiplying the norm with the magnitude of alpha. Can I just complete this? Yeah. And the third, which is a triangle inequality, x1 plus x2 norm is less than x1, a norm of x1, so norm of x2. Okay. So now the general claim we are making is any norm ball with center xc and radius r is a convex set. Okay, including so if I define x norm, x or p inverse induced X norm as square root of X P inverse X. Implies ellipsoid is a P inverse induced norm ball centered at XC. Right? Is visible? So, centered at XC. There's a norm ball centered at XC. This is just the P inverse norm for X. So if you want to call it X tilde. Now this, what we are saying here is this X tilde is X minus C for the ellipsoid. Not necessary. In fact, AD will not be symmetric. But A should be non-singular. A inverse should exist, basically. Okay, so to I've just kind of elaborated on what this notion of a norm ball is. The norm ball with center XC and radius R is a convex set. Now, how is it? Again, there are some 6 steps I've talked about. So 6 basically sequence of 6 kind of steps of decomposition, and then we show 1 is less than or equal to 6. Okay, so how do you do that? The first is you take lambda x1 plus 1 minus lambda x2 minus xc. Right? Our goal is to prove that this is less than or equal to R. That's our goal, right? You want to show that this 1 is less than or equal to 6. Have filled in the intermediate steps. This is assuming that x1 minus xc norm is less than or equal to R. x2 minus xc norm is less than or equal to R. Right? So just for any norm, this is basically we want to show that x1 plus lambda exponential. Okay, so to fill in all these intermediate steps here, we invoke the properties of norm. That's all we are doing. Okay. So you can quickly tell me what properties are we invoking. The first step is I'm just doing lambda x1 okay, plus 1 minus lambda x2 minus lambda xc. The same xc I'm taking with lambda and 1 minus lambda. Have I used any property of norm so far in this first step? Nothing. Xc is is lambda xc plus 1 minus lambda xc. Nothing at all. Second step. What have I done? So the parts in green I've combined, right? Lambda x1 and lambda xc. I combine them into lambda x1 minus xc. And then 1 minus lambda x2, 1 minus lambda xc is 1 minus lambda x2 minus xc. Any property of norm have I used here? No. Then what have I done here? Next step. Lambda x1 minus xc. So it's lambda x1 minus xc and 1 minus lambda x2 minus xc. Oh, I made a mistake here. So let me use. Just a second. So all I've done here is added, I will put these. Which property of norm have I used here? Sorry. So I have used which property? Sorry again. The triangle inequality. Right. I've used this triangle inequality. Well, is it only this triangle inequality? I've done something more. I've actually done 2 as well, right? So I've combined 2 and 3. So first, by triangle inequality, lambda x1 minus xc and 1 minus lambda x2 minus xc should have been multiplied inside the norm. But I boldly took them outside by virtue of step 2. So I've combined steps 1 and 2. Right. So what have I done? Using properties is I have basically used this properties 3 and so properties 2 and 3 in translation from expression 3 to expression. Okay. After that, it's very simple. X1 minus 1 minus xc is less than equal to r. Norm of x1 minus xc, norm of x2 minus xc is less than equal to r. That's it. That's just simple. You got it? It's a very simple proof. So this is quite useful. If we can show that anything is any function is a norm, then it's norm ball is a convex set. So I've kind of summarized this entire derivation here. To prove 1 less than equal to x follows from assumptions 4 less than equal to 5, 3 is equal to 2, green becomes pink and yellow becomes gray and so on. Okay, so ellipsoid is defined using P, or P inverse. It doesn't matter, P or P inverse. Here I use P, in the board I use P inverse. Euclidean ball is a simple 2 norm. Okay, so this is just showing this thing in a little bit more detail. And also I kind of hint at why the relation between A and P inverse comes up. Okay, now we move on to convex functions. And we'll do a little bit more on sets as we develop further on functions. The the definition of a convex function is inherently tied to a convex set. A function f is convex if the domain is a convex set first. And why is domain required to be convex? Because we are going to consider all kind of convex combinations of points in the domain. And for every such convex combination of point in the domain, we need that the function evaluated at that convex combination should be less than equal to the convex combination of the function values of those 2 points. Simple English, plain English. What we'll of course often deal with is slight variants of convex functions. Like you have strict convexity, strong convexity, and so on. And the norm that we have just showed on the board turns out to be an example of a convex function. Okay. So we'll see that if f is a convex function, fx less than equal to c is a convex set. Okay. That's what we showed there, right? A norm one. So let's just write this down so that if domain f is convex and for all xy the domain of f fx plus 1 minus lambda y, it's just f evaluated at the lambda x plus 1 minus lambda y. If this if this is less than equal to this line segment joining, or below, if it's below the line segment joining fx fx2 y fy, which is basically amounting to saying that f at the convex combination is less than equal to lambda fx plus 1 minus lambda fy. Then f is convex. Convex function. It is a convex function. Okay. Now the slight variant on the board is that the gap is strictly greater than 0. So if this gap, right, if we have strictly greater than 0, then we have strict convexity. Okay, so basically saying that this, if it's strictly less than, then f is strictly convex. Now there are other variants where you look at the gap being strictly greater than 0, but also as a function of how far x1 is from x is from y. Okay, so there's a third notion so I can say that, well, a third notion is less than what we have on the right hand side plus. Okay, so I want that this is less, but it is less by some margin, some proportionality of x minus y square. Okay, that makes it strongly convex. The same expression on the right hand side, but something c by 2 into norm of x minus y square. So you're saying that the gap is not only strictly greater than 0, but guaranteed to be greater than right? Sorry, this should be minus. This is minus here. Because it's less than there. So you're saying it should be less than x minus 2 norm square. At least that much gap. Sorry? Yeah, I'm just saying that we'll come to that. This third part I have not written on the board. You understand strict convexity, right? The notion of strong convexity is a slightly more nuanced, slightly more specific form of strict convexity. Right? They say, oh, strict convexity said, okay, there is a gap. Strong convexity says, oh, that gap is at least so much. Is at least so much in terms of a function of a quadratic function of x minus y. Right? Is this clear? The intuition is clear to everyone, right? Now you could look at other characterizations. These are some well-known, well-studied, often motivated from quadratic functions themselves. Right? So just again re-emphasizing, domain of F must be a convex set, right? So domain of F is required to be convex because function at all convex combinations is required. Otherwise, you can't even talk about convexity there. And then the second part is here, right? So z is less such that f of x is less than or equal to z. Now this part, what you're seeing on the screen here, this itself is also convex set. Okay. What I'm now, the additional perspective I'm bringing there, I'll use the same color, there's blue there, right? So I'm saying that the perspective now is that the space lying above the convex function is also a convex set. So it's also called the sublevel, I mean, it's actually epigraph, epigraph. So epigraph is a set. If the function goes from xn to r, then epigraph is an xn plus 1 in a slightly high dimensional space. Right? It's the original function is going from x to r, right? It's one function of one dimensional input. So this f is going from real to real. Whereas this blue set is in R2, this blue set. Set of all points above the set. That also happens to be a convex set. Very intuitive. If the function is convex, the set of all points above the function is convex. So do you see that the connection between convex functions and convex sets is actually not just incidental. There are a lot more connections. Okay. We'll see that the notion of separating hyperplane or supporting hyperplane is very closely tied to the notion of gradients or subgradients. Right. So if if you have this set, then you can think of a supporting hyperplane somewhere here, and that will correspond to gradient of the function. Okay. So I'm just trying to show you lots of connections. It's okay if not everything is registered, but as long as you understood what was written on the previous slide, that's we are good to go. Yeah, and I also emphasize that this gap itself might be characterized in terms of some quadratic guarantee. Okay. I'm assuming you're at least glancing at the videos before the class, just so that you have some head start. Okay. Okay, so strongly convex functions. Now a little bit more on the strongly convex functions. I'm retaining this thing norm here because as you would expect the norm is a convex function. So norm is one of the typical examples of convex functions. But before we get there, what is strict convexity? Oh, sorry, strong convexity. I showed there that strong convexity would mean that there is a guaranteed gap. But here's another way of defining a strongly convex function. A function f is strongly convex if there exists a mu greater than 0 such that the function gx obtained by subtracting mu by 2 times norm x square is convex. Okay. So you should try and show the connection between these two definitions. Okay. So strong convexity on slide. On the slide, what is the notion of strong convexity? Fx is strongly convex if gx, which is equal to fx minus mu by 2 norm square, is convex. Okay, this is a strong convexity on slide. On board, which I have defined there, right? I've used green color there as well. F of lambda x plus 1 minus lambda y is less than equal to lambda f x plus 1 minus lambda fy minus, I think c by 2. I can use c by 2 first. Can I use c by 2? Yeah, I use c by 2. Minus c by 2 norm of x minus y square. This is 2 norm. By default, when I use norm without a subscript, it is 2 norm, L2 norm. So question for you guys, you can think about it. Connection between mu and c. What is the connection between mu and c? Here we have c, here we have mu. Right? What is C definition telling you? The C definition saying, well, the gap between the line segment and the actual function value is at least x minus 2 norm square. What is the mu definition saying? Oh, the function remains convex even if I subtract a quadratic mu by 2 times norm of x square from the original function. In that case, the function is called strongly convex. What do you think is the connection between the two, mu and c? How many of you think they're the same? They'll be equal? Will be the same? Sorry? Linear multiples? Some mystical linear multiple, or I think it'll just be, or do you think it'll be just a simple two times or whatever, right? Some fixed linear multiple. You try working it out, yeah. Sorry? Lambda? Why should there be a lambda? Huh? Yeah, can you think and work out? I think I'll have it. Yeah, so the reason I bring this definition is for any convex function, the function fx plus lambda by 2 norm x square is strongly convex. What does that remind you of? What does that remind you of? Right. But what does it remind you for machine learning? Is lambda. So basically putting a regularizer gives you strong convexity. Right? Okay, so now the connection between the two. So I've given some homework here. Derive the term T such that f of theta x1 plus 1 minus theta x2 plus T is less than equal to theta f of x1 plus 1 minus theta f of x2. Basically, that term T should be connected to this, right? To this. So you have to derive this term T. That's your homework. Okay. This is my term T on the slide. It should be, I mean, the term T will be of this form, right? And the other thing is, if a function, if it's strongly convex and G is convex, but not necessarily strongly convex, then adding the two brings you strong convexity as per this definition, right? So if one function is convex, the other is strongly convex, that means from that strongly convex function, if I even subtract mu by 2 norm x square, I still have convexity. And that term mu by 2 norm x square, I could also subtract from the sum. and still have convexity. Right? So this gives you a very quick way of assessing, its utility for utility for machine learning regularizer, how it helps you bring strong convexity. It quickly gives you an idea of how summation of two functions, one strongly convex and other just convex, gives you still strong convexity, and so on, right? Like hinge laws. We'll see that hinge laws is not differentiable. But you add an L2 regularizer to hinge laws, you suddenly get strong convexity. So actually, L2 regularizer to hinge laws actually makes it much better behaved. Okay. So yeah, so you can, these are your homeworks. Homework 1 derive this term T. Homework 2, you have to show this, right? Using the hint provided below. Okay. So this is very simple, not very difficult. But I'm giving these homework so that you really sit and write. These are very simple homework problems. Okay, so I mean, I've kind of given you some solution steps here, not completely. Right, I've basically shown that the function f is strongly convex if there exists a mu greater than 0, that the function gx is equal to fx minus mu by 2 norm x naught square is convex. So I have kind of tried, and basically I've shown you how c should be the same as mu. But this is written slightly differently. But I would like you to sit over it and convince yourself. Okay? So all you have done is done a lot of substitutions here. That's it. So if you substitute for gx in terms of fx, gx is convex. Substitute in gx for fx at x1 and x2, and you'll basically see that difference. The difference term in terms of the term t will come up in terms of mu by 2 norm x squared. It's not very difficult. Okay, I'll leave you to the homework problem. So now more examples. Examples of convex functions. So linear functions are convex A transpose X. Right? Very simple. You substitute. So all of this by first principles. Why is A transpose X convex? Well, if I have A transpose lambda X plus 1 minus lambda Y less than equal to lambda A transpose X plus 1 minus lambda A transpose Y. Very simple. It's equality. Affine functions. I put a B there. A transpose X plus B will still hold. Exponential function. We'll see a little bit of that, but exponential function also. Exponential functions behave like this, right? They're cup shaped. Right? So we'll show you some tools, but every norm is convex. Why? The same proof will hold, right? What we use for norm ball being a convex set will still hold for the norm function. Like same steps. A little bit more involved. It may be because now you have to deal with x1, x2. But it's not difficult. Yeah. So recap how we proved that the norm balls are convex sets, right? So we said for any x1, x2, and b, then you should have like these steps, remember. Now, the steps are going to be very similar. Right? So you're just going to show this. This is what you want to show. Theta x1 plus 1 minus theta x2 is less than or equal to theta of 1 x1 plus 1 minus theta of norm x2. And you don't have an R here, that's all. Everything is the same. So in fact, the sequence of steps is a subset. Right? You need to just have this step from this step until this step, basically. Right? You don't have an XC, that's the only difference. You don't have a center. In norm ball, we had a little bit more work also with respect to center. So it's very simple. I'm sure you can prove this. Okay. So every norm is convex just basically by triangle inequality. Triangle inequality and homogeneity of the norm, which is f of alpha x is alpha f of x. These are the two properties we have used. I've just summarized the proof method here. The details are exactly for norm one. Any questions? Right. So it follows that for every norm function, this will hold. Now we'll look at some more. Okay. So let's start listing down all the functions that are convex, because that will be very handy when we start analyzing. Okay. So convexity, we have some graphs. Let's start listing down convex functions. In fact, listing down convex functions, strong convexity, you can also think of strong convexity. So step number first one was linear affine that entire group, right? Second is norm. Are all norms strongly convex? What do you think? Not necessarily, right? Which norm would you think is strongly convex? L2. Basically, it's match fixing, right? Heads I win, tails you lose. So we already decided that in strong convexity, the gap is characterized by L2 norm. So you're not leaving so much choice. But there are matrix induced norms, L2 matrix induced norms. They can also be strongly convex. Like the Euclidean, the ellipsoid was using a P inverse norm. So because that is based on an L2 norm, right? That's also strongly convex. So so linear affine norms, but I'll just make a slight note here. Um, Matrix induced norm. But then P matrix induced for P, you need some symmetric positive definiteness property. Okay, so let's look at some examples, more examples. Okay, non-negative weighted sum. So let's say I have alpha 1 for convex function 1 plus alpha 2 convex function 2. All the alphas are greater than equal to 0. And that will also be convex. Okay, so this is a property. So I'm going to distinguish the property from list. Okay, so this is, okay, let's use the right side of the board. Okay, so the first is non-negative weighted sum. The second is property is composition. So if f is convex and ax plus b we know is affine function. F of ax plus b is also convex. So all you need in both these definitions is f to be or fi is to be convex, nothing more, right? So therefore, say norm ax plus b, 2 norm or any norm is convex. Now it turns out that log of bi minus ai transpose x is convex because minus of log x is convex. So log is convex. We'll show how log is convex. For log to be convex, you can also use first principles. Not difficult. Log x is convex by the first principles. And log of bi minus ai transpose x, minus of log of bi transpose ai minus x, is convex because it's a composition, right? It's composition of a function with an affine transformation of x. Okay, well, let's look at more. Now, this is a slightly tricky one, but this is very helpful. The third property. Okay, I'll anyways write down log here. So the list of convex functions. Now the third property, or compose a kind of property slash calculus, you can call it calculus of convex functions, is in terms of f of x being convex under certain conditions on h and g of x. Okay, so composition. So composition is convex if g is convex. Convex g with non-decreasing convex h. It will not be increasing, but non-decreasing. Or the other option is concave g, and you also need h to be convex. So h remains convex in both cases, but in the second case, h becomes non-increasing. A relaxed version of decreasing. Okay, let's just pictorially understand how to prove. We'll show it, we can show it by first principles. I'll do it on the slides, not on the board so much, but I'll give you an intuition what's happening, right? So just look at the annotations there. So the first one basically is saying that G is convex, but H must be convex and non-decreasing. So it must be like this. Or optionally, G can be concave. I don't have another pen for that, but yeah, let's use it. G can be concave like this. But in this case, H continues remaining convex, but non-increasing. Okay, just remember these combinations. You can actually draw the, if you have color pens, right? This helps you remember. Now, what's really happening? H is, see the function